Hello everyone and welcome back. My name is Mr. Koval, and in this video I'm going to be going over instantaneous rates. So in my last video I was talking about average rates. There we just took the average change in time versus the average change in the concentration of a substance, and we divided them so it was the change final minus initial, the concentration of a substance divided by the final minus initial of the time. Here we're going to find the instantaneous rate where instead of getting a range or an average between the ranges of rates, we want to get what is the actual rate at a particular point in time. And so here that's called the instantaneous rate, and we'll show how to do that. So let's get into this. So instantaneous rates. The average rate, as I was saying, tells us the speed of a reaction over two time points, right? So we get a final point, an initial point, and we figure out what the difference in those points are. But if we want to know the rate at an exact time point, that's going to be our instantaneous rate. We're going to have to calculate that. Well, how do we calculate that? Well, here's an example. We have this reaction. We have C4H9Cl plus water is going to give us C4H9OH plus HCl. And so here's a graph, and it's showing the change in the concentration of your C4H9Cl. So on the y-axis here, we have the concentration in molarity, and on the x-axis we have time. And so here you could see the change in the concentration of your C4H9 Cl. So it's a reactant. So we're going to start with a lot of it. So it's 0.1 molar at 0 time. And when the reaction begins, so our initial rate at time 0 is going to be here. So as the reaction goes, though, you could see that it's decreasing, which is what we would expect. So the reactant is decreasing because it's forming product, but you'll notice that its slope decreases as time goes on. It starts to curve and flatten as time goes on. And so the slope here is what is measuring the instantaneous rate. So we can get the slope of the tangent line that is touching our curve at the particular point that we're interested in. Then we could calculate the instantaneous rate of time by drawing a triangle. And so here you can see here, we could figure out the instantaneous rate by this tangent line, this dotted line here. And then versus at a later time, like 600 seconds, we get the slope at the line here. So we want the tangent line, the line that's touching the curve at our point, and we want a straight line there. And we could figure out what the slope is by our triangle that we draw here. Same thing here. If we want to know the rate of change, the instantaneous rate of change at 0, then we would draw our triangle here, get the tangent line here, draw our triangle, and we could get the rise over run slope, which is the hypotenuse of our right triangles. Okay, so this is going to be a plot of concentration over time, so we're going to need that. So the next thing is that we are going to need the slope of a line tangent to the curve at any point, and this is going to be our instantaneous rate at that time. So the tangent line, the slope of the tangent line at the point of interest is going to give us the instantaneous rate of time at that time. So if we're interested in the instantaneous rate of our reaction, instantaneous rate of change, in our reactant at time 0, then we're going to need a tangent line at that point at time 0 here, and do our little triangle. If we wanted to know at 600 seconds, then we draw a tangent line at that point, so it's touching at that point, and draw our triangle. And oops, sorry about that. And then we would calculate the slope by figuring out what the rise over run is for our triangle. So you get the change in our concentration of C4H9Cl over the change in time, whatever that is. So the reaction slows down as time goes on because the concentration of reactants decreases. So steeper slope means it's going faster. So here we have a steeper slope, right? So the reaction rate is going pretty quickly here relative to down here. You can see that the slope of the tangent line is less, and therefore it's slowing down. The rate is slower here because we have less reactant to react. Remember, you need the more particles you have in a solution, the more they're going to bump into each other, the more they're going to react. But as time goes on, you're removing reactant, so less collisions, less reactions. Okay, so steeper slope is going to be faster. More less inclined slope is going to be slower. So the instantaneous rate at 600 seconds is going to be slower than the instantaneous rate at time 0. Okay, so those are the two comparisons. All right, so again, instantaneous rate is equal to the slope of the tangent line to the curve at a specific point, the point that we are interested in. So usually a point in time. So the tangent line is a straight line that touches. Tangent means touching, right? So a straight line that just touches the curve at that point and has equal angles on both sides. So what we mean by here is that the angle between the curve and the line here on this side of the point is equal to the angle and the curve on this side of the point. So we want our tangent line to be drawn so that it is touching at only that point of our curve, and that it's straight and not crooked. So basically you want the angles here to be equal. Okay, we're not talking about the angles of our triangle, we're talking about the angles between the curve and the straight line on both sides of the point. Okay, so remember, slope is rise over run. That's going to be important. Oops, sorry about that. So make sure when you draw your line, make sure that your tangent line is not sloppily drawn. Again, make sure the angles are equal. All right, let's do a practice problem. Okay, so what is the instantaneous rate at 30 seconds for the decomposition of hydrogen peroxide? So here we have our slope for our graph. We have a little graph here of concentration and molarity versus time of the amount or concentration of hydrogen peroxide. So we're looking at the decomposition of hydrogen peroxide. So because hydrogen peroxide is decomposing over time, we're getting less of it as time goes on. So we start here at 1 molar concentration. As time goes on, that concentration is going to decrease because the hydrogen peroxide is decomposing into probably oxygen and not hydrogen, but probably water and oxygen. Okay, so it's decreasing over time. So we need our concentration versus time curve, our graph here, and we're going to look at the change in concentration of hydrogen peroxide over time. So, and our rate, we're interested at 30 seconds. So that's our point of interest. So at 30 seconds, this is our point. You can see it crosses over at 0.4 molar. So at least as far as I can see. So here is where we want to draw our tangent line. So our tangent line is going to be drawn here, and we're going to do our triangle. So there's our point. We're going to put our point there. So you can do this on your sheet of paper. Okay. And then you're going to draw your line. So there's our tangent line. And again, it should only touch at this point. Now, of course, when you're drawing your line, it's going to look like it's, touching at more than one point, and then probably is, but just do the best you can. You just want it to cross at that point here. So this is where we're going to make sure that our point is drawn, and we want to make sure that the angles on both sides are equal. So we want both sides of the point to have equal angles. Now here, when you draw your triangle, you have a couple of options. You can choose to draw your triangle so that the points of your triangle, the vertices here, the points of your triangle at the ends are crossing at a well-known point that has a line, right? Another thing you can do is you can draw the tangent line all the way to the x and y axis and see where it crosses over, and you could have your triangle, the legs of your triangle or the sides of your triangle be the axes themselves. So you could draw your tangent line until they hit the axes, and then you could use that triangle. Or you can draw your tangent line until they hit a point on the graph where two lines intersect, and you can know that point. So this will make your calculations easier. Another option you have, and this is this is a legitimate and maybe even a better way. You could draw your lines to the axes. You don't necessarily have to, but what you can do is you can measure the distance using a ruler between 2 points on your graph here. So like between 10 and 20 seconds, I can use a ruler and I can measure the distance between these 2 points, and I can get a relationship between, say, between 10 and 20. That's a 10 seconds interval. And so I can see, oh, well, let's say I'm measuring this in millimeters, or I'm measuring in centimeters. I can see what 10 seconds is equal to as far as the length goes, right? So let's say I measure the distance between here as, I don't know, 15 millimeters. Well, now I can have a relationship between the distance 15 millimeters and 10 seconds, or a second. So I can get a relationship between seconds and distance of measurement. I can do that here on the y-axis too. I can measure between the two numbers here, these two spots here, and that's between 0.4 and 0.2, and I can get a relationship between 0.2 molar versus a distance. Or maybe this is again 15 millimeters, maybe it's 10 millimeters on the x-axis. So I have a relationship between 10 millimeters of distance is equal to 0.2 molar in concentration. So once I get those relationships between time and distance measured using my ruler, and I get a relationship between molarity and distance measured by my ruler, then what I can do is I can draw my line, and I can then measure the lengths of the two sides of my triangle in, say, millimeters, and then convert those millimeters into time for my x-axis and into concentration for my y. So that's another thing you can do. Okay, so let's move on and draw our triangle. So there's our tangent line. Again, we could draw the tangent line all the way to the axes. And so you can see here it crosses over, it looks like at 0.8 molar. here it looks like it crosses over at 60 seconds. So you could use this distance here and this distance here to do your rise over run. Or you could just draw the triangle from on these lines here. So you could draw that line and then draw this line and draw your triangle here. So whatever fits, whatever you think is best. And then here's our triangle. So now all we need to do is get the rise over the run. So what's the difference in the concentration here? So the rise over the run is final minus initial. So here, final minus initial. Final, since we're decreasing, final concentration is going to be here at 0.1 molar. Our initial concentration is going to be at 0.7. Looks like 0.7. Again, and final minus initial for time is going to be the final time is 50 seconds. Initial time is 10 seconds based on where we stopped with our triangle. And so now we can do our rise over run. So we put the rise, which is concentration. That's our y-axis. Remember, rise over run. And so we got our 0.1 molar minus 0.7 molar gives us its number. So that's going to be a negative 0.6 molar. And then we get our 50 seconds minus 10 seconds, which is 40 seconds. We divide those and we get a negative 0.1 or 0.015 molar per second. And so that's our rate, or instantaneous rate of change for this example. And it's negative because the rate of change is decreasing. So our instantaneous rate of change is going to be negative because we're decreasing in our product. I'm sorry, we're decreasing in our the amount of reactant that we have. So it should be negative. That's what the negative is telling us. And that, ladies and gentlemen, is how you do it. So we have this concentration, right? Just to point that out. So the top is where we get our rise over run. The bottom is where we get our change in time. And so that's how it works. So that's it for this video. The next video, as you just saw, is going to cover rate laws. So thanks for joining me. I hope you enjoy this video. I really hope you learned something from this video, and I hope this was helpful in any way. If it was, please, by all means, subscribe to my channel. Hit that like button. Also, make sure you share this with your friends. And also, when you're subscribed to my channel, hit that notification bell and then click all so you can be notified by all the videos I put out. And finally, put a comment down in the comment section. I would love to hear from you. Ask me questions. I'd love to answer your questions. Thank you very much for joining me, and have a great day.